In the previous video, we understood why memory is unsafe. In this video, we'll look at the classic memory bugs that keep appearing again and again in operating systems, browsers, kernels, and mobile apps. These bugs are decades old and they are still causing real world exploits today. We'll discuss one by one. So, first one is buffer overflow. A buffer overflow happens when a program writes more data than the buffer can hold. Memory does not know the boundaries, it just writes to the next address. So if we see the example of buffer overflow, you can see we have defined a buffer of size 8, but we are copying a longer string. If you count, this is a 12 character string, and we are copying it into the buffer size of 8. And if we run this program, let's first compile it. You see a simple warning, it does not crash. And if we run, you can see it compiles and the compiler didn't stop us. And it prints the value also. After that, it is giving us abort result. So the program may crash or may not. There is a possibility. So the behavior is undefined and this is harmful. Then the next bug is out of bounds. Sometimes the program does not write outside bounds. It only reads. That sounds harmless, right? But it's not. This reads memory. So we have defined array of size 3 and you can see 3 elements are there, 10, 20 and 30. But the value we are printing 5 index, which is out of bound of this array because we have defined 3 size. So the valid indexes are only 0, 1 and 2. But we are trying to access 5th index, which is out of bound. So this reads memory that does not belong to the array. And you might leak secrets, pointers or keys. This is exactly how Heartbleed worked, a famous memory bug. So if we try to run this, let's use the previous command and change this to out of bound. And see, you are getting the warning, but it didn't cache. And if we run this result, then you see we are getting this value printed as the 5th index of this array. The compiler doesn't stop us or does not crash. In runtime also, we ran this code and we got this garbage value. So this is a kind of undefined behavior. This program may crash also. So this is harmful. Now, the next is use after free. And this is the most dangerous bug. We have discussed in the previous video also. This is one of the most dangerous memory bugs because everything looks normal here, right? The pointer still has an address which we have freed, but the memory is no longer ours. Another part of the program may reuse it. Now you are reading or writing someone else's data with this pointer, right? Because after freeing, this pointer does not have this value which we have defined. But still, if you try to run this, gcc and uf.cpp result, then you see no compiler error. And if we run this result, then you see the normal value also. It is printing normal value 4. We haven't defined any 4 value, but we are getting it. So this is a kind of undefined behavior that attacker can misuse. So this is very dangerous bug. Now let's talk about next bug, which is double free. Freeing once is important, but freeing double is a kind of bug. Freeing memory twice is just as bad. Memory allocators maintain internal data structure. So once we freed the memory, okay, the internal data structure will be updated. But double free corrupts those structures if we are freeing double, like 2 times. And this can lead to crashes or exploitation. So if we run this program also, double free, and yeah, result, no, the compiler gives no error, no warning. It runs through it, right? And now we are getting the crash. Trace step dot result, and this is we are getting in runtime. So this is harmful, and the behavior is undefined. We don't know what is going to happen. So heap corruption is also possible, and overwrite, like the structure will be corrupted. The memory allocators can also be corrupted. Now the next is type confusion. This one is subtle. Memory has no idea about types. We told the compiler to trust us, but the memory layout doesn't match. If you see, we have defined two structures, A and B. We have defined one value to this parameter, X parameter of struct A. It has a value. Now we have defined struct B to be as struct A, which has only, if you see, one member. Struct B has two members. So once we assign struct B to A, so B only has the memory of having only one integer, right? But it has two integers. But if you see, we can define the value. We can assign 100 to the second value, which does not exist in the memory. We are using someone else's memory, right? This kind of bug is very dangerous in kernel. We'll see later how Apple and Cherry try to stop this. And the important question is, why these bugs are keep coming back? All these bugs share one thing. The system trusts the programmer. Memory doesn't enforce bounds, lifetime, or type. So the same mistake repeats in different forms. Now we know the enemy. So the next logical question is very simple. Can we detect these bugs while the program is running? You saw all the memory bugs that I have shown you. Compiler does not stop us. For some bugs, it may give us warning, but when we are running, we see undefined behavior. So the question is, can we detect them? That's where AddressSanitizer comes in. In the next video, we'll see how ASAN does exactly that. And remember, we'll keep it simple.